You clicked because you heard that everything in C is undefined behavior, and you need to know what that actually means for your AI pipelines. The stakes are higher than a simple crash because this behavior causes silent data corruption that destroys model accuracy without raising a single exception. By the end of this video, you will understand why the compiler is actively hiding the bugs that make your production inference fail unpredictably. There is a persistent myth that undefined behavior in C is just a rare edge case or a compiler quirk that only affects hobbyists. That perspective is dangerously wrong for anyone working on high-throughput AI inference. The C standard explicitly defines 193 specific cases where the rules simply do not apply. This is not a suggestion. It is a formal contract between the programmer and the compiler that says if you violate these rules, the compiler can do absolutely anything. In a debug build, that anything might look like a crash or a warning. In a release build optimized for speed, that anything becomes a silent transformation of your data that you cannot see coming. Consider the strict aliasing rule, which is one of those 193 cases. This rule states that you cannot access an object through a pointer of an incompatible type. In practice, this means you cannot cast a float pointer to an int pointer and read the value. If you do, the compiler assumes that never happens. It will optimize your code by reordering memory accesses or removing what it thinks are redundant reads. For a simple calculator, this is fine. For a neural network processing thousands of tensors per second, this optimization can cause the GPU to read garbage values instead of the actual weights. The result is not a crash. It is a model hallucination where the output is statistically indistinguishable from data drift, but the root cause is a pointer cast you wrote 3 months ago. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Now consider the problem of shifting by the width of the integer type. If you have a 32-bit integer and you shift it by 32 bits, the C standard says the behavior is undefined. The compiler is free to assume you never do this. It might optimize the code by assuming the shift result is always 0 or by removing the entire conditional check. In an AI inference loop, this often happens in pre-processing steps where you calculate bit masks or alignment offsets. If the input data causes a shift equal to the width, the compiler has already deleted the safety check. The pipeline continues, but the data is corrupted. You might see a sudden drop in inference accuracy that you cannot reproduce on your local machine because your local compiler or optimizer settings are different from the production environment. This creates a hidden state problem in distributed systems. A program might behave perfectly on a debug build with sanitizers enabled, but fail unpredictably in production where aggressive optimizations are turned on. The 193 cases of undefined behavior create a gap between what you think the code does and what the machine actually executes. This gap is where the real danger lies. The compiler is not being malicious, it is following the standard to maximize performance. It assumes undefined behavior never occurs, so it can eliminate checks and reorder operations. But in high-throughput systems, that assumption becomes a systemic vulnerability. Think about the cost of safety checks. Adding runtime bounds, checking, or aliasing guards to every array access and pointer cast in an AI kernel adds significant overhead. Architects often decide that the performance cost is too high. They rely on the assumption that the code is correct and that undefined behavior will never happen. This is a gamble. When a single integer overflow or pointer cast in a pre-processing step occurs, it invalidates the entire batch of inference results. The system does not stop. It continues processing corrupted data, leading to a cascade of errors that are difficult to trace back to the source. Sanitizers like Clang can help detect some of these issues, such as shifts by width or out-of-bounds access. However, they are not a silver bullet. They often miss subtle lifetime violations or floating-point trap representations in optimized builds. The primary knowledge gap lies in quantifying the exact frequency of these silent failures in large-scale inference systems. Most data comes from isolated bug reports rather than comprehensive production telemetry. We know these bugs exist because they have been found in the wild, but we do not know how many are slipping through the cracks every day. The real insight here is that undefined behavior is not just a compiler quirk. It is a critical source of non-determinism. It turns rare edge cases into deterministic performance bottlenecks or silent data corruption under load. When the compiler exploits undefined behavior to eliminate redundant code paths, it can inadvertently remove critical synchronization logic or data validation steps. This is especially dangerous in AI inference where data patterns are highly correlated. The optimization might remove a check that was guarding against a specific input pattern, and suddenly that pattern becomes a trigger for silent failure. The solution is not to avoid optimization or to rely on sanitizers in production. The only viable mitigation against unpredictable runtime behavior is strict adherence to the standard. You must treat the 193 cases of undefined behavior as hard constraints. If you cannot guarantee that your code avoids these cases, you cannot trust the results of your high-throughput pipelines. This requires a shift in mindset. You must stop viewing undefined behavior as a rare exception and start treating it as a systemic risk that requires active management. This approach changes how you design your kernels. You stop assuming that the compiler will catch your mistakes. You stop relying on the behavior of a specific compiler version. You write code that is robust across all standard-compliant compilers, even if it means sacrificing a fraction of performance. The trade-off is worth it when you consider the cost of debugging a silent failure that only appears in production under specific load conditions. The next time you write a pointer cast or a bit shift, pause and ask yourself if you are stepping into one of the 193 cases. If the answer is yes, you are not just writing C code. You are writing a time bomb that the compiler might detonate at any moment. The only way to ensure reliability in your AI inference pipelines is to eliminate that uncertainty. Treat undefined behavior not as a compiler quirk, but as a critical source of non-determinism that must be engineered out of your system. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.